In this lecture, we're going to start on our new section of stress. So this follows our discussion of strain. And I always find stress kind of interesting in the fact that most undergraduate courses talk about stress right away in the class, and then later on they talk about strain. To me, strain is much more physical. You can see the effects of deformation. You can see things stretching out if you have a rubber band or you pull on things. But with stress, we really can't see stress. It's just a mathematical definition. It's an important definition to use, and it's very useful in engineering. But we just can't get that same kind of physical feel. That said, when we talk about strain first, it almost seems a little bit weird because we already know so much about stress already in your first courses in engineering and mechanics of materials, strength of materials, and so forth. Well, we're going to define stress as the intensity of force. So it's of great value in engineering because it allows us to relate spatially varying deformation fields to the distribution of applied force throughout a body. We'll do that through the use of what's called a constitutive equation, something that relates stresses and strains to one another. Obviously, when we put a load on something, it will deform. Okay? So stress and strain are related to one another. But for our discussion, we're going to focus on stress. And stress has come about through these loads. Loads can be thought of as being transferred through a body one plane at a time with equal and opposite forces acting on each side for bodies in equilibrium. And so what I have in this picture is something you'll often see in elasticity books. This is an arbitrary three-dimensional body. Looks like a potato, but that potato shape is supposed to represent any kind of specific three-dimensional body that we want, like an I-beam or a plate or something like that. And on this body, I have some forces that I'm applying to it, here and here. I also have some restraints. Something that will keep it attached to ground. Right? Now, when these forces are applied, we can think of these forces as transmitting themselves through the body and to the supports. Now, there are non-equilibrium situations where you may have accelerations, and we'll talk about that briefly. But mainly for our class in elasticity, we're going to take a look at bodies that are in some sort of equilibrium state. Well, the way that gets transmitted through these different planes is through the stresses in the body. And those stresses themselves, although they're distributed through the body, if we were to pull a plane out of this body, here it is here, we would have a force on the top surface of the plane, and we could have a force on the bottom surface of the plane. And we would realize that those are equal and opposite forces through Newton's laws. If we were to pull out that plane and take a look at it, if we look at just the one side of this, we're only going to look at the one applied force on the top surface. It may be kind of skewed to the surface. Okay, so that would be the general force F. I don't want the subscript N on there right now. But we can take that general force F and we can break it up into two different components. One component lying in the plane and the other component lying perpendicular to the plane. So we can have a normal force and we can have a shear force on that plane, and resolving that general force F into those two components allows us to identify normal stresses and shearing stresses. Our normal stresses are going to be given by the letter sigma, and it's going to be the normal force divided by the area of that plane. and our shearing stress is going to be the shear force divided by the area of that plane. And these are average normal stresses and shearing stresses on the plane. We're taking that entire resultant force and averaging it out, spreading it out, smearing it all over that particular area A. The distribution may not actually be uniformly distributed over the area A, in which case we can take a look at the stresses at a point where sigma would be the limit as a small amount of area goes to 0 of a little bit of force over that little bit of area, and the shearing stress would be the limit as that small amount of area goes to 0 of a little bit of shearing force divided by the little bit of area. So if I wanted to show that on this picture, maybe there would be a little spot right here where we could call delta A, and there would be a small bit of normal force and a small bit of shearing force at that particular spot. Now, of course, the units of stress then would be force divided by area, pounds per square inch, newtons per square meter in the different unit systems, or we would call that PSI or a Pascal in the standard British Standard or the metric system. Now, in addition to these forces that are acting on our body directly, we can also have acceleration fields or long-range forces that act on the body. So here's my three-dimensional body again with some restraints, a couple of forces on it. But in addition to this, we may have this sitting in a gravity field. It also could be accelerating. So we call those long-range forces. Now, the contact forces are sometimes called short-range forces. Okay, so these would be the short-range forces that we might have. And if we have a gravity field, then that would be subjected to the volume of this body, and that would be a long-range force. Well, the next thing we want to do is we want to apply, essentially apply Newton's law of motion to a continuous three-dimensional body. And to do that, I'm going to sketch out my three-dimensional body, and I'm going to put a specific coordinate system in here. We'll see later on that, of course, this would exist without a coordinate system. We have this three-dimensional body. Here's my x1, x2, x3 coordinate system. We're going to call this body region R, the three-dimensional body. We're going to take a look at a little element that is somewhere on the surface of this body. So maybe this is kind of curved over here like this, and it's just going inside into the interior of this body just a little bit. That's going to be our volume element. I'm going to call that dV. It has a little bit of volume, dV. And on this surface, we'll call that ds. And acting normal to that surface pointing out of the body. That will be our unit normal that we will call N. Okay, so Newton's law of motion is effectively F is equal to ma. And what we're going to do is we're going to take a look at what happens to that small representative volume element, and then we can integrate that over the entire body. There's a few things that we need. We need to know the density of the material. That's how the mass term is going to get incorporated into this. Doesn't have to be constant. Okay? But for now, we'll just say rho is the density of the material. We'll need to know what the body forces per mass are. We'll call these B. So it's not necessarily, it can be the weight. Well, we're going to incorporate the weight through this term, but the body force could be something like a magnetic field or something like that. So this would be a body force per mass. We want the units to work out in such a way that we're going to call the little b a body force per mass. And then A is going to be our acceleration field. This was shooting off somewhere and accelerating. So in this case, if we wanted to think more about those long-range forces, that act on that little volume element, we're going to have the body force vector term. Because it's a body force per mass, we're going to multiply that by the density and then the volume, since the density is a mass per volume type term. Now the short range forces, or the contact, is going to be given by something that acts on this surface N. And we're going to call that the traction vector T. That is the function of that unit normal N. And then the contact force then will be the traction as a function of the unit normal times the area on which it is acting. Okay, so the traction vector, it has units of stress. It has a slightly different interpretation in certain cases, but that traction vector then will have like a force per surface area. So if we multiply it by that surface area, then we'll get the force that's acting on that particular region. So we're looking at that small volume element, so we're only going to multiply that by the surface area that we see there, ds. Okay, so let's make a note that this is the traction, and then this is the force when we multiply that by that small little bit of area there. So if these are the forces that are acting on that small volume element, then if we apply our summation of forces equal to ma, effectively, what we can get then is on the left-hand side, for the entire body, we're going to have a volume integral of rho times the traction vectors B dV. Okay, that's our long-range forces, plus our short-range forces that we're going to integrate over the surface. Now, it's common sometimes in some texts to denote the surface as partial r. Okay, so this would be the traction as a function of the unit normal integrated over the surface. And then on the other side we have the MA term. If we integrate over the three-dimensional body the density times the acceleration times dV, then we have everything on the right-hand side. So these are volume integrals, and this one is a surface integral. This is often called the balance of linear momentum. Okay, so we think of a lot of things being conserved. We can talk about the conservation of mass. In other situations, it may be more appropriate to call that the conservation of mass and energy. But the conservation of linear momentum and the conservation of angular momentum are a couple of ideas that we will use to help us get to where we want to learn a few things about stress. And just to make a note of it here, that T of n terminology means that the traction vector depends on n. It is not a it's not a multiplication. Okay, so the traction vector T is a function of n. Now, oftentimes for graduate students, when I give quizzes or examinations before they start on their research, one of the things I always like to ask is this: what is the conservation of linear momentum? What is the equivalent of the summation of forces equal to ma for a three-dimensional continuous body? And so this would be the starting point. You would identify the long-range and short-range forces and the accelerations of the body and put these integrals together. Now, this form that we have right here is perfectly fine. It's not completely useful for us right now. We're going to take a side detour, and we're going to explore what this traction vector as a function of n means. We're going to do something related to what's called the Cauchy tetrahedron. So let me sketch that up. It's going to take it just a moment to draw, but it'll just be a quick pause on the video. Alright, so there's the tetrahedron. Tetrahedron is a four-sided object, and so what I've done is I have the coordinate system x1, x2, x3 with the unit basis vectors e hat 1, e hat 2, and e hat 3 right there, and then at some skew angle is a plane that intersects those three coordinate axes. And so what we're looking at right now is the front surface of that plane. And so with a few more additions to this, this will be known as the Cauchy tetrahedron. And this discussion is taken from a book called Theory of Plasticity Theory by Lubliner. It's available in a Dover edition, a very inexpensive edition. It's a pretty nice book on plasticity, and at the beginning of that he goes through and does some basic continuum mechanics. And so that's where I'm drawing this information. Now we're going to fill in some items on this tetrahedron. One of the things that we need is a unit normal displayed on here. And so if we can think of a unit normal bursting through from the origin, this unit normal that I'm going to draw here is perpendicular to this inclined plane that I've got. That inclined plane is going to have an area of delta A. And we also have areas on the three back faces of that tetrahedron. And the way that we're going to label these is that the area perpendicular to the x1 axis is going to be called the delta A1 area. The area perpendicular to the x2 axis is the delta A2 area. And then the third one is the delta A3. Now, acting on these three planes are tractions. Three planes in the back are the tractions. There's also another traction that acts on the front. Okay, so let's see if I can find a good color to use here. I guess we'll go with the red. I don't want to be too confusing. So we can think of the large plane, the delta A plane, having some sort of traction vector acting on it, and it is skewed to any three of the axes. It doesn't even have to be aligned with the unit normal. So I'll call this traction vector T, but remember it depends on the unit normal, so that's the T of n term. On the three back faces are also traction vectors. So let me draw the one that's here. Maybe it's off in this direction. That is the traction vector, and it is a function of the unit normal to that plane, which is the e hat one direction, but it's actually in the minus direction. So it's a function of minus e hat 1. Okay, likewise, there's some other traction here. Remember, these have units of stress. So that is on the A2 plane. That is the normal would be the minus e hat 2 direction. And then the last one, somewhere over there maybe, is the traction as a function of minus e hat 3. Now there's no such thing as the equilibrium of stresses. The summation of stresses equal to 0 is not a thing. But there is a thing called the equilibrium of forces. The summation of forces equal to 0. So if we want to use that idea of equilibrium, we need to convert these tractions into forces. We do that by multiplying them by the areas on which they act. So let me use the dark color. This traction acts on the total front area, delta A. This one is acting on the area A3. This one is acting on the area A2, and so forth. So now we have forces right there. This little piece of body may also have acceleration fields, may have long-range forces that act on it. We've defined those terms already. If the body force per mass vector, the density of the material, the acceleration, and this traction term depend continuously on position, and if the tetrahedron is small, our integral over the body of rho b dv is going to be approximately equal to rho b delta v, the volume of that little object there. Likewise, integrated over the body for the accelerations. We have the mass per volume times the acceleration times dv. That integral is approximately going to be equal to rho a delta v. And then when we look at the surface term, the traction as a function of the unit normal n times ds is going to be approximately the summation of these four forces that we have right here. Now I'm going to write this in a special way here. The traction vector on the front face plus the other three terms, I'm going to use the summation of the traction vector in the minus e hat j direction times delta a j. Okay, so that's just those four force terms added together. If we wanted to write them all out, this right-hand side then would be equal to traction vector as a function of the unit normal n times delta a plus traction vector minus e hat 1 times delta a1 plus t times minus e hat 2 times delta a2 plus t, I said times, but as a function of the minus e hat 3 direction, delta a3. All right. Now at this point we're going to make note that there is a relationship among the sides of the tetrahedron. Okay, so if we have our coordinate system here, and here's our tetrahedron, we have our unit normal n that has components of n1, n2, and n3 in that coordinate system. Then it turns out that the area of each of the three sides is the unit normal component times the area of the front face. Okay, so delta A1 is equal to N1 times delta A. Delta A2 is equal to N2 times delta A. Delta A3 is equal to N3 times delta A. Now I have a supplemental video where I use something called Heron's formula to show that this is the case. If you can set it up right, you can also think of vector projections of areas. But for now, we'll just note that the area delta AJ is equal to the NJ component of that unit normal. It has to be set up this way with these three perpendicular coordinate axes for our Cauchy tetrahedron. But delta AJ is equal to NJ times the area delta A. So my integral of this traction term here, we can say that T as a function of N can all be written in terms of the area A. We can have a plus T as a function of minus E hat J NJ times delta A. Now this is getting a little awkward with this minus E hat 1, 2, and 3 direction. Again, this is an implied summation here. It's getting a little awkward with that notation. So we're going to do something. We're going to rewrite this notation just a little bit. As this notation will be the same as the notation I'm going to write here, minus t sub j in j. So this is a traction vector, either 1, 2, or 3. That is the same kind of notation as what we had previously. It's the negative of t as a function of minus e hat j. Alright, so where are we going with this? Well, let's go back and look at our equation. We have a volume integral of rho b dv plus a surface integral of our tractions equal to a volume integral of our acceleration, our ma term. And with the approximation then of a continuous region and so forth, we can rewrite this as this term t of n minus tj in j plus rho b minus a delta v by delta a is approximately equal to 0 when we put all the terms on the one side. And when we reduce this down to a point instead of a finite region, this ratio of the volume to the area tends to 0. The volume will go to 0 faster than the area. Which means that this term is a linear function of n. Okay. So it's the nj component to the first power, not a higher order power. In fact, that that's a linear function is going to help us out here in just a moment. Now this is kind of a detour. I don't usually ask students to go through this level of detail, but we're going to use that then when we take a look at our Cauchy tetrahedron again, and we break up the tractions on each of the faces into particular directions. Okay, let me make a new sketch. And so then looking at those tractions again, we have our tetrahedron, we have the traction on the inclined face, and we have the tractions on the perpendicular faces. It's important to note that with this notation that I have here, the t with the squiggle underneath of it means a vector, and so we're looking at 3 different vectors. We're not looking at the components of a vector, we're looking at 3 different vectors. And so we're going to define a term sigma ij as the projection of that particular traction vector into the unit basis directions. So for example, on the one face, we're going to have a projection of T1. Let me use a different color. In the one direction. That is going to be our sigma 1, 1. We're going to have a projection of T1 in the 3 direction and in the 2 direction. So I drew the 3 first. Okay, this one would be sigma 1, 2. See that one very well. Sigma 1, 2, and this would be sigma 1, 3. And likewise, we're going to have a normal and two shears on each of these three back faces. And those will be the components of what we call our stress. This traction vector then is going to be the sum of our three components of our traction vectors. Okay. Well, let me say that a little differently. This traction vector right here has three components itself. It has components T1, T2, and T3 in the E hat 1, E hat 2, and E hat 3 direction. Now, notice here I'm not putting the squiggle underneath of this. These are scalars. These are scalar components. So it has a scalar component T1 in the E hat 1 direction, T2 in the E hat 2 direction, and T3 in the E hat 3 direction. So let's write this down. This T of N has these three components. I'm just going to write what I just wrote down again. But it's also equal to what we had before, the three backface traction vectors, 1, 2, and 3, times their respective unit normal component in J. So suppose we want to find this component T1. What we're going to do is we're going to take our vector and dot it with the E hat 1 direction. So our vector, this T right here, has those three components, T1, T2, and T3. We're going to dot it with the unit basis vector in the 1 direction, 1, 0, 0. Okay, so obviously we get T1, but we would have to get the same operation as if we dot it with this right-hand side as well. It's also the same as the E hat 1 vector dotted with Tj, Nj. Let me make a little bit of room here. But we've defined this E hat dotted with this other term just right here. We just did that. So E hat 1 dotted with Tj is what we're going to call sigma 1j. And if we did E hat 2 dotted with Tj, then that would be our sigma 2j and so forth. But in this case, our T1 component would be equal to sigma 1j nj. Our T2 component would be equal to sigma 2j nj. And our T3 component would be equal to sigma 3j in j. In general then, if we use another free index, we can say that the ti, now this is the scalar component of this oblique traction vector, the ti component is equal to sigma ij in j. In direct notation, traction vector t is equal to the stress tensor times that particular unit normal. If we want to use matrix notation, these components of the traction vector could be found by doing a matrix multiplication At this point, we don't know that the stress tensor is symmetric. There will be an additional restriction that we'll have to apply. So it would be this matrix times the unit normal components of the oblique face. Right. So there's a lot of subscripts and squiggles going around here. Let's just emphasize again. This vector has three components. Its three components are little t1, t2, and t3. No squiggle underneath of it. We can find the first component by taking that traction vector dotted with E1, just like we do here. But that's also equal to E dot 1 dotted with the right-hand side, since these two things are equal. There is an implied summation right here, Tj in j, where the squiggle underneath this t means that these are the vectors on those back faces. If you kind of step back from all the details, it makes a lot of sense. It's just the summation of forces equal to 0 effectively. We have to throw that in j in there so that we can get the areas to work out right, so that we can get forces. All right, so the components then of the front face, the oblique face, traction vector T1, T2, and T3 can be written in terms of stresses in N1, N2, and N3. So we'll end up using this relation, this traction vector relation, quite a bit. It's a little bit different symbols than what our book uses, but the traction vector components then is equal to sigma ij in j. There's a couple important things to remember when we use this particular formula. All of these terms must be using the same coordinate system. These are components. It's not a component-free version of this equation. So these are specific, tied to a specific coordinate system. So these must all use the same coordinate system. I've seen people mess this up. Sometimes it's because they are thinking of things in different coordinate systems. So we put on here when expressed as components. The other thing to keep in mind is that this unit normal in must be a unit normal. In order for that to all work out. Alright, now let's go back. We took our little detour. Let's go back to our equation, conservation of linear momentum. We have our long-range forces, we have our short-range or our contact forces. We have our acceleration field. The body is flying off. You can write this again. But now, in terms of traction vector components, hang on. I switched over here to indices instead of vectors. Okay, so for particular components, then we can write it this way. Traction vector terms here can be replaced with sigma ij in j. And actually, I don't need that squiggle underneath this one either. Sigma ij in j Okay, now we have two volume integrals and a surface integral. We really want to have this in terms of all three being the same type of integral. We're going to convert the surface integral into a volume integral. We've talked about how to do this already. If we remember the divergence theorem, in general, a volume integral in the form of del dot some vector or tensor A dv can be rewritten as a surface integral of A dot within ds. And if you look at the sigma ij in j, that is in the form of an A dot in. If we were dealing with components, we would write it this way. The volume integral would be partial derivative of A sub I with respect to x sub I dv would be equal to an integral over the surface of A I in I ds. So we're going to rewrite this then as a volume integral rho bi dv plus a volume integral. We can write it as the partial of sigma ij with respect to xj dv. So we'll rho a sub I ds. If we want, we can use our, I should use consistent notation with my volume integrals. This is over a three-dimensional region R now. If we want, we could also write this as rho bi dv plus integral over that three-dimensional region. We can use our comma notation for partial derivatives. So we have sigma ij comma j. We have a rho ai ds right here. We make a little bit more room. At this point, we can collect like terms. Okay, they're all volume integrals. So I'm going to lead off with the stress term, sigma ij comma j plus rho bi minus rho ai dv is equal to 0. And if we have an integral of something equal to 0, and if that something, that some region that we're integrating over is arbitrary, then the integrand must be equal to 0. So let me write it this way. If the integrand holds for all regions, then the integrand is 0. And so what we get then is sigma I j comma j plus rho bi. I move this to the other side, is equal to rho ai. And these are known as the differential equations of motion. If the body is in equilibrium, the ai terms are 0. And in that case, we have sigma ij comma j plus rho bi is equal to 0. These are known as the equilibrium equations of a three-dimensional body. If we can ignore the body force terms, then this reduces down even more. Sigma ij comma j equal to 0. And it's just another expression of the equilibrium equations. Let's write these down in kind of a long form instead of with our index notation. Now remember, with our index notation, we have a repeated index. So this is actually representing 3 different terms. And we have a free index that's the I term right here. Alright, so let's expand this out. We can use numbers or we can use letters. I'm going to use the letters term. It's more classical to write these with letters, and I'll show you how we're going to write this body force term as well. But our first term would be like the partial derivative of sigma xx with respect to x plus the partial derivative of sigma xy with respect to y plus partial derivative of sigma xz with respect to z plus a body force term, and I'm going to call that capital X. So that would be like rho b1 then equal to 0 for equilibrium. Okay, I'm going to go ahead and write down these others. We have a y term, capital Y, and then the last one as we have here. And again, these are the equilibrium equations. So there's a couple ways that we can use these. We can use these as a set of differential equations that we can solve for these fields. Or, if you have the field, you can check to see if it really does satisfy equilibrium. And the second approach is actually maybe a little bit nicer than the first approach, although we will use both in this class. But if you had a stress field that was a function of x, y, and z, and you took the appropriate partial derivatives, and knowing what the body force terms are, or if they can be neglected, then we have a set of conditions that have to be true if that body really is in equilibrium. Those 3 partial derivatives and the body force term had to be equal to 0 for each of these 3 lines that we have here in our equilibrium equations. Now you may often see these written slightly differently. You may see this as a partial derivative sigma xy with respect to x. But at this point, we don't know that the stress tensor is symmetric. We're going to investigate that occurrence pretty soon when we take a look at the conservation of angular momentum. All right, so I think that's enough for this lecture, but we'll pick this up, like I said, with the conservation of angular momentum. We'll be able to show that the stress tensor is symmetric, and then that'll kind of make life a little bit easier. I should say we'll be able to show under what conditions the stress tensor is symmetric.